All right, so on this next one, because it's an even power, you guys have told me we're going to use one of these, right? So I need to write this in terms of sine squared. Anytime there's an even power, I can write it as sine squared raised to something, right? So I would write this as integral of sine squared of x to what? 2. Right, and if that had been like sine to the 6th, sine to the 8th, sine to the 10th, whatever, I just do sine squared to whatever I have to do to multiply those to get that number. If it was sine to the 10th, that would have been a sine squared to the 5th. And now, I use that identity. Use the, what I call the, why did you do that? Use the double angle formula is what I was going to write. That's what these are basically called, double angle formulas. So I'm going to use that here. So I get the integral of 1 half and times, now sine squared is the minus, so I have 1 minus cosine of 2x, all of that squared, dx. So I'm using the double angle formula. Now you got to square both parts of this. So I've got a 1/4 that I'm going to pull out front, right? Because if you square the 1/2, you get 1/4. And then you're going to square this guy right here. 1 minus cosine of 2x squared. Which we're still not out of the woods yet in terms of how complicated that integral looks like. What would you do next to try to simplify that integral? Yeah, FOIL. I can't do substitution yet. I mean, you might be thinking along the lines of let's go ahead and try a substitution now. The problem is if you let u be anything inside there like the cosine of 2x, you're going to need a sine to handle the differential, right? You're going to need, when you do u, you're going to have a sine in it. And I don't have that. So the only thing I can think of next to do is to try to multiply that out. So I get 1/4 integral. Can y'all do that in your heads? Minus, well,
minus cosine.
one minus, yeah, there's going to be 2 of them is the thing, because the outside and the inside.
Yeah, I was skipping that step.
Cosine 2x times 1 minus cosine 2x. First, outside, inside, and last. So the outside and the inside give me minus cosine 2x, which is minus 2 cosine 2x. And then plus a cosine squared of 2x dx.
So you just add the 2 in the middle here.
Yeah, to get the middle term. Now the good news is, and I'm going to underline it in green, this is easy to integrate, right there, that 1. This is easy to integrate by substitution. Okay, this is a problem right here. Because it's a square again, right? And if you did a substitution or whatever, anytime you got a power of a trig function, you've got a mess. So if you don't have a power of it, then you can just use substitution.
So you just use your identity?
Do it again. Yeah, exactly. Now use that identity. Double angle again. Because it's an even power. So you get 1/4 integral of 1 minus 2 cosine of 2x plus, now 1/2. And now instead of, notice up here on this formula, sorry I'm scrolling up for just a second, you got it at the top of your page hopefully. Cosine squared of x is, nope, I went too far. Cosine squared of x is 1/2 1 plus cosine of 2x. So if I had a 2 in here, what do I have right there? A 4. Replacing x with 2x. Does that make sense? Okay, so down here, This now cosine squared of 2x would be 1/2 times 1 plus cosine of 4x dx. Okay, so I don't have a square to worry about like I did up here on this one. What I do have is this 1/2 that I need to distribute.
What made you put 4x right there?
The formula for cosine squared of x was 1/2 1 plus cosine of 2x. So if you have cosine squared of 2x,
Oh, so you just
then I've got to put a 2x inside here, right? Which gives me 2 times 2, which is 4x. I don't know why I did that. How about we do this? Started in the middle instead of on top and tried to salvage it and turn it into something whack. Okay, so here's what I've got: 1/4 out front. Now what I'm gonna have here is a 1/2 plus a 1/2 cosine of 4x, right? I can combine this 1/2 here with this 1 here and have 1.5 or 3/2 minus 2 cosine 2x plus 1/2 cosine of 4x dx. All right, so that's 1/4. Now I think I can do all these integrals now.
Can you pull the 3/2 out too?
Well, the 3/2 is not times everything, right? Whereas the 1/4 up here was multiplied times the whole inside. So this 3/2 is just a 3/2 by itself, not times everything. So I can't factor it out in that sense. Okay, integral of 3/2.
3/2.
Can you do negative cosine of 2x in your head? You know the integral of cosine is sine, right? Derivative of sine? No, derivative of sine is positive cosine. So your integral of cosine is positive sine. Yep. So the sine is going to stick around. It's going to be sine of 2x.
Would be 4 sine.
Now when I take the derivative of this, I need to get a 2 out front. So I don't need to put anything in front of it, right? Check that. Is the derivative of negative sine of 2x, it is negative 2 cosine of 2x, right? By the chain rule.
Okay.
I'm figuring out what has to go in front here, which is a 1. So I get a 2.
Now, if we were just cosine of 2x.
I'd have to put a 1/2 out front.
That's what I thought.
Yeah.
Why would you put a 1/2 up for?
If it was just cosine of 2x, right? If I was trying to do the integral of cosine of 2x dx, I would know it would be a sine of 2x. But what do I have to have out in front so that whenever I multiply by the derivative of what's inside, I just have a 1 out front, right? Because when you take the derivative, right, you need to make sure that you apply the chain rule. So I'd have to put the 1/2. But I don't have to do that in this case, because there's already a 2 there. Now, what I'm doing is that I'm doing substitution in my head. If you want to do this the long way, you would say, okay, integral of negative 2 cosine of 2x dx, let u be 2x. Then du is 2 dx. Okay? So here's your du, and here's your u. So you have the integral of cosine of u with a negative out front, u du, which gives me negative sine of u du, which is negative sine of 2x. I don't know why. Integral of negative cosine is negative sine, and you just substitute back in. All right, let me follow that same argument on this next one. I know it's going to be plus. The integral of cosine is sine of 4x. But I need something right here that when I multiply by 4 gives me a 1/2. So I'll put a 1/8 there. Right? Because when I take the derivative of this, I need to get 1/2 cosine of 4x. So sine of 4x times 4 needs to equal 1/2. So there we go. Close integral plus c. I'll close bracket. Which is good enough, or you could distribute the 4. I mean, this is acceptable right here. Or 3/8 x minus 1/4 sine of 2x plus 1/32 sine of 4x plus c. All right, so questions about that? You know, we went down a couple of roads there. The main one is that we had to apply this double angle formula twice. Other questions?
And then you didn't take the derivative until you got to.
Yeah, until I got nothing squared, no powers of the trig functions. Okay, so when there's an odd power, I think that's a little bit easier to me. You strip it off and then turn it into it's basically a polynomial in U. When there's an even power, you're going to have to apply the double angle formula until you don't have any powers. So we applied it twice. And that works for sines and cosines. So this table, or this box that I've got on the next page, is basically a summary of that. If the power of the cosine is odd, save one of your cosines and then turn the rest into sines. If the power of sine is odd, save one of your sines and then turn the rest into cosines. And then do a substitution. If they're both even, you use the half angle identities, or what I call the double angle identities. Same idea. Use these identities.
Now, do we have one of those for every trig?
For sines and cosines.
Just that.
Yeah. I'm about to move on to tangents and secants. Okay, so yes, we've only covered now a third of our trig functions to be able to do these types of tricks. And we won't actually be able to do every possible combination, but we'll do as many as we have the tools to be able to do it. So now let's talk about when tangents are times secants. Okay, what's the derivative of tangent? Secant squared of x. So we can separate out a secant squared of x factor, and then there's actually a Pythagorean identity for the relationship between secants and tangents. You remember this one, right? Sine squared of x plus cosine squared of x equals 1. Remember that? From before, right? Now, if you divide everything by cosine squared, what does that give you? There's a tangent squared, right? So you can separate out, if you have enough secants to do this, you separate out a secant squared factor instead of just a secant now, and then convert all the rest of the secants to tangents.
Now, did you get the tangent identity from the sine squared over?
Exactly. So this is tangent squared, and this is secant squared. 1 over cosine is secant, so 1 over cosine squared is secant squared. So this identity right here lets me replace secant squareds with tangents. Actually, 1 plus tangent, right?
And so tangent squared x plus 1 equals secant?
Yes. Yep. That's,
So anytime I see tangent squared x plus 1, I can change
yeah.
it.
But really, we're going to be going this direction.
So the other way.
Yeah. So really, what you care about is taking the secant squareds and replacing them with tangent squareds of x plus 1. That's
Why
really...
Why would you want to make that move? Is tangent easier to work with? Than secant?
Well, the idea is the same thing we did up here, like with the sines and cosines. When I stripped off a cosine and turned everything else into tangents, into sines, then I did a substitution. Let u be sine, and the result was something like this that only had u's in it. And then the du was cosine of x. So now what I'll do is I'll take off the secant squared off to the side, and then everything else will have tangents and secants in them. But I can turn all of the secants into tangents. So now everything depends on tangent with what's left. And so I'd let u be tangent, and then du is secant squared tangent of x. And I'll use that leftover secant squared that's sitting over there to go into my du.
That's the same we were talking about earlier, like you can't do one thing without the other, right? Earlier we were talking about
Which part? Which problem was I on
like what?
when I was talking about that?
We were talking about that like you can't like take the you can really use the sine or something like that without cosine. It's like
Right. So if I've got a cosine squared or a sine squared, I can't just do, if I got a power of one of those trig functions, I can't just take the integral of just that function without the other one being there for the substitution. That's what I was trying to say, yes. So same idea in the sense that if I've got tangents and secants both there, I'm going to let u be the tangent, and then because I've pulled the secant squared off extra, I can use that in my du. This is a good example right here. This example right, I would let this become a secant squared of x times a secant squared of x dx. Now I've got this off to the side, and I've got a tangent to the 6th x over here. Okay? If I let this now turn into tangents by the 1 plus tangent squared of x, or tangent squared of x plus 1. I'll write it the same order I had it before. Tangent squared of x plus 1, right? This becomes that. Notice how what I've got is a tangent to the 6th x, a tangent squared x plus 1 times a secant squared of x dx. Okay? I peeled off a secant squared, and now everything over here depends on what? Tangent. So I would let u be tangent of x. If u is tangent of x, what's du? Dx. There's my du. And everything over here now, I can replace all the tangents with u. So I get integral of u to the 6th, u squared plus 1 du. I can eliminate all of my trig functions when in that case.
I guess I just don't understand how the identity helps because you still have a square in the identity and change it like tan square.
Right. As long as what's left behind is an even power, I can always use that trig identity to get down to a tangent right? So I mean, if what's left behind, I mean, think of any of these. If I've got a secant to the fourth x, like I did right there, I split that into secant squared of x, secant squared of x, dx, okay? There's my leftover. I can turn this into tangents.
Right.
If I had a secant to the sixth x dx, right? I would have a secant to the fourth. I would peel off a secant squared of x dx. Now I can turn this into secant squared of x squared. And I can make that 1 plus tangent squared of x squared.
Right.
Then I can replace that with u. I mean, it's okay that it's squared, because what I'm going to do is replace it with u.
Okay, so
And then I don't have trig functions to worry about at all.
So the U's what?
The u substitution is what's making this work.
Because I was like, we were doing it earlier, and you were like, well, squares are bad, and then we have this.
Right, squares are bad with trig functions, but if I can do a substitution to get rid of them, that's good. But I can only do the substitution if I can peel off what I need
Okay.
to make the du.
Makes sense.
That's what I did in the first part of the sines and cosines. So if I had odd powers of cosine or odd powers of sine, I could peel one off and turn the rest into everything else, into sines. I peeled off a cosine, or turn them all into sines. Sorry, all into cosines if I peeled off a sine. Okay? Problem now is what happens if I did this. Secant to the fifth of x dx.
It's just
This doesn't work. Yeah.
Take off one
But
and then split.
yeah, the problem is that taking off one doesn't get me anything that a u would turn into a du, because it's not squared, right? I'd have a secant squared of x dx, but I got a secant cube of x that I got nothing to do with. I can't apply that. So this technique will work with even powers of secants times anything of tangent. Okay?
Just multiply everything by inverse. Have an inverse multiplication method.
If only we could just multiply in functions of x anytime we wanted to, life would be easy, but we can't. We can only multiply in constants. Well, then you're solving a different integral.
It wouldn't be correct, but we could do it.
True. Yes.
That's Frank. Like say secant 5, see how you got secant,
That's a square.
I mean, no, I'm talking about, nah.
Go ahead.
Cause you could be secant 4 and then secant 1, and that would work, right?
If I did a 4 here and a 1, that is true. That is equal to that. But there is no substitution u where du gives me a secant x dx. Right? My goal is to somehow turn this into a trig function that I can stick here,
Multiply in tangent.
and then when I take its derivative. But the only good choice right now is tangent, and the derivative of tangent is secant squared. So the reason I'm peeling off a square is because it is that thing that is the derivative of tangent. Okay? I mean, the goal is so that whatever I do to my u, to get my du, that this guy right here, I could then replace with all of du. But there's nothing that goes here that is, when I take its derivative, just gives me secant.
Is there anything that you can take that will give you secant to the third?
Nope. Okay, so the point is, right now, what can you handle? You can handle so far, and I'll give you some more. We're not done with all of our strategy. But you can handle odd powers of cosine, odd powers of sine, even powers of cosine, and even powers of sine, and now, even powers of secant times tangents.
You can't handle that just yet.
But what about odd powers?
We're about to find out.
We're about to find out that sometimes we can do that depending on what the tangent is. What the power of the tangent is. Watch this. Can y'all finish this integral?
Yeah, I think so.
This problem should be easy from that point forward, right? Because it's now u to the 8th plus u to the 6th. Integrate, power rule, piece of cake, plug your thing back in, right? I mean, I think you can almost do that in your head. It's going to be like 1/9 tangent to the 9th of x plus 1/7 tangent to the 7th of x plus c.
And use a capital C.
Do what? I think that's the answer to that one.
Yeah, it ought to be.
I mean, you boom, u to the 8th plus u to the 6th, which is 1/9 u to the 9th plus 1/7 u to the 7th plus c, which, and then you substitute back in. What are we gonna do with that secant 5? All right, so look at this guy. This one's a mess. He's a problem child. Okay.
Get rid of the whole thing.
There's another identity up here that I've left some blanks. We got to go back. I'm going in roundabout order. What about the derivative of secant? Does anybody remember what the derivative of secant is?
Cosecants.
Nope.
1 over 1 minus x squared.
Yeah.
What? Tangent secant, or secant tangent.
Oh, we're doing the inverses.
I don't think there's a square in
The inverse is 1 over.
It's just secant tangent. Okay? You can look that up on a table, or you can do it the long way to prove it.
You're gonna give us a table?
Yes.
Just
Yes.
write the table of what you said.
Table of derivatives. I won't give you a table of intervals just yet. Tangent. Sorry, what am I doing? I'm going to explain to you why the derivative of secant is that. So secant of x, by the way, is 1 over cosine of x. So if I said take the derivative of this, it's the same as taking the derivative of that, right?
Yeah.
Can you take the derivative of cosine of x to the minus 1? This is just a Cal 1 refresher.
Same thing.
Okay, take a derivative now. I'm not doing integrals. So ignore 7.2 for a second and go back to your Cal 1. How do you take the derivative of this?
I would have just.
How do you take the derivative of x to the minus 1?
Put it up.
You do this,
One to the front.
bring that out to the front, increase that by 1, right?
Yeah.
So you get negative x to the minus 2.
Yeah.
That's all I'm asking. What's the derivative of this then?
Negative cosine.
Negative
Cosine.
times cosine of x to the minus 2 times the derivative of what's inside. Derivative of cosine is
Sine. Negative sine.
negative sine.
That's what I would agree. That's it.
There you go. Minus becomes a plus. So I actually have a sine of x over a cosine squared of x, right? To the minus 2.
Yeah.
Which is sine of x over cosine of x times 1 over cosine of x. Which is tangent secant. Exactly what we wrote up there. Okay.
I would differentiate it by quotient rule.
So we can separate a tangent of x, secant of x factor, and then if what's left we can write in terms of secants, we're good. So this identity let me turn secants into tangents. So how might I turn tangents into secants?
And the secrets.
Secants. Secrets. Oh, what a great idea. Secant squared of x minus 1.
New math.
Using this same identity, which is basically this guy up here, just moved the 1 to the other side. Okay, so here's the idea. Up here on this one, if I could separate out off that secant squared, and what was left was an even power of secants, I could turn them all into tangents and then use the substitution u equals tangent. And that's what I did on that first example. Now, if I can separate off a tangent secant, both of them together, and if what's left behind has even powers of tangent, I can turn them all into secants and then use u equals secant as my substitution. All right, let's try that. Way down here. Odd powers of secant. What's my strategy? Only thing I have to do is peel off a secant and a tangent together. So I need a secant, or sorry, tangent of x, and the secant of x that I'm separating out. And what's left? How many tangents? 4 of them, and how many secants? Okay, now my goal down here is to use u equals secant of x, because du is now secant of x, tangent of x, dx. Right? That makes this whole thing my du. But now I need everything over here, okay, in terms of secants. If I can do that, then I can just do u equals secants, and this whole thing turns into just u's. No trig functions to worry about. So I'm going to use, the secant to the 6th is fine. I need to use this guy. So
then you split it.
I'd call that tangent squared of x squared.
And then you do
Secant squared x minus 1 squared. Okay, so that's equal to the integral of secant squared x minus 1, quantity squared, times the secant to the 6th x, times the tangent of x, secant of x, dx. And again, I've got this whole thing here. That's my du. And now this becomes u squared minus 1 squared times u to the 6th. So my integral now is
so when
what do I have? U squared minus 1 squared times u to the 6th du, right? When that happens, that's where you take a nice sigh of relief that all the trig functions are gone. You enjoy that fact, that you've eliminated them from the integral completely. And this is now easy in that it's just a polynomial.
Now they just changed the use back to the
After you integrate. So multiply everything out, distribute everything, and then it's an easy integration. Right? Can you multiply out u squared minus 1 squared?
that's 4, right?
Just FOIL. Yep.
It'd be u to the 4th minus u to the 4th, right?
No.
4th minus 2u squared.
U to the 4th. Outside. Inside. Minus 2u squared. Plus 1 is all times u to the 6th. That makes sense, Matt?
Yeah.
distribute this. U to the 10th minus 2u to the 8th plus u to the 6th du. So this is the easy part. 1 over 11 u to the 11th minus 2 over 8 or 1/4. Nope, 2 over 9, sorry. 2 over 9 u to the 9th plus 1 over 7 u to the 7th plus c.
And now, is that acceptable with the U's, or do you want?
No, you got to substitute it back in.
Okay.
Yeah.
So I did that all in one step.
1 over 11. What was our u? Secant? Secant to the 11th of x minus 2 over 9 secant to the 9th of x plus 1 over 7th secant to the 7th of x plus c. Oh, the power. Okay, so think about what we have the ability to handle now and what we don't have the ability to handle. For secants and tangents, when secants are even powered, we can do any of those when they're times a tangent, right? Now, when can we use the second rule? Well, it's when the power of tangent is odd and you have a secant, right? Because on this one, I had to be able to pull off a tangent and a secant and then turn the remaining tangent into a secant. So I can handle when I have even secants and when I have odd tangents with a secant. If I have an odd tangent without a secant, then all bets are off so far. But that's the next table that I've got. So, if the power of secant is even, then save your secant squared, turn the rest into tangents. If the power of tangent is odd and you have a secant, then save a secant tangent and turn the remaining tangents into secants. And then do the substitution, u equals secant. Okay? And for the rest, I don't have very good rules. This is the good line right here. The guidelines are not as clear cut. So those are the easy cases we've covered so far. Now you have to get creative with the rest. We may need to use substitution, I think is the blank. We need to use integration by parts. And maybe need to use a couple of known integrals.
This homework should be fun.
Do what?
I said this homework should be fun.
Oh, baby. There are 11.
Hey, close though.
Yeah. Just twice, plus 1. Okay. Most of them, I'd probably say 7 or 8, maybe even 9, are like previous examples in this section that I've given. Okay. With maybe 3 or 4, 2 or 3, that require some more creativity than that. All right, so first of all, look at this next one that I've got on the screen here, and identify or convince yourself why it doesn't fit into any of our categories that we have to us so far. It's by itself, so it's an odd power of tangent, but there's no secant to split off a tangent secant. So this second strategy, part B, would not apply because I need a secant to be able to do it. But it's actually not that bad if you play with it. First thing I would do is write this as tangent squared of x times tangent of x.
Pretty much anytime we see an odd number, you split.
Not guaranteed. I'm going to do an odd one down here. Oh, I didn't even do it. I'm going to do one anyways, because we still have the secant to the fifth that's a weird guy, and I'm going to have to do something about him. Turns out integration by parts is the trick that works on odd powers of secants. All right, let me get us to the point where we can actually see maybe some light at the end of the tunnel, and then I'll dismiss and we'll come back at 11. This right here, I would write as secant square root of x plus 1 times tangent of x. Right, that's that identity that says tangent squared can be written as secants. And then I distribute this. So what I really have here is the integral of secant squared of x tangent of x plus tangent of x dx.
Secant squared x minus 1.
Oh, minus. Thank you. Minus here, minus here. Minus. Now here's the good news. This guy right here fits the criteria of our second strategy. And this one, I have a formula for. Boom, there. And then use B from strategy above. That's where you separate off the secant tangent. Then you'll just have a secant left, which you can use as your substitution. U equals secant. Dot, dot, dot. We'll finish that, and then work some of these. And some integration by parts, by the way, when we come back at 11 and do some problems together. I'll stop working them and let you start. I know you're psyched about that. All right, so we're dismissed. I have one other set of examples that I'm going to do real quick at the beginning. These are easy, by the way. Compared to everything else we've done, those are the easy ones. Yes.